Hello, welcome to lecture for week 4 on regression analysis. So this week, we're going to look at bivariate, multivariate, and logistics regression. With me again, Dr. Yanto Chandra from the City University of Hong Kong. Just to go to some basic terminology. In the previous week, you have heard about different types of descriptive statistics. And what we did last week was very much what we call univariate statistics, in which we were only interested in a single variable. We were not quite interested about relationships or causality. We look at the means of a particular variable, the frequency of another variable, the variance, standard deviation. We plot some graphs, some quartiles. Those are what we mean by univariate statistics. Now, in bivariate statistics, it means means it always involves two variables at a time. For example, when you are looking at the relation between two variables in a correlation, you are already involved in bivariate statistics. Or if you're doing a very simple linear regression between one variable and another variable, this is also considered as bivariate statistics. A more advanced type is called multivariate statistics. This is where the statistics involve more than two variables. And it is perhaps considered as a much more advanced way of explaining relationships or even testing causality. For example, you wanted to know what factors that drive people to buy and sell things on the internet, right? To be an e-commerce entrepreneur. And there can be like, what, 50 variables that can explain what somebody need to have in order to be able to be an e-commerce entrepreneur. So you will not use these 50 variables. You can narrow them down to a smaller number of dimensions, and that is what we call factor analysis. And we'll cover that in week 8, or it's a couple of weeks from now. And that is one example of multivariate statistics. You can also do a more complex regression. For example, you have multiple independent variables. Let's say you want to use age, education, gender, and let's say the GPA score in predicting someone's salary, right? So you have multiple independent variables and one dependent variable. Or you can even have multiple dependent variables, not only the salary, but also happiness, and what else? Ability to climb higher in their jobs. So you can have multiple dependent variables, right? And you can also do things like what we call choice modeling, or for example, choice experiment. For example, you want to know what drives people to choose a certain type of car, right? Because when people want to buy a car can be constituted or can compose of multiple types of variables, right? You can have colors, different colors, let's say 5 different colors. Price, you can have low, medium, and high. Maybe country of origin, where it is manufactured. Let's say Germany, Japan, US, China, etc. So you can have multiple. So, and also, let's say fuel efficiency. You can have, let's say, low, medium to high fuel efficiency. So you can have multiple types, and for each type you have multiple levels. And this is a much more complex type of variables which can be studied as part of multivariate. So if we want to say which type of statistics are more analytical, then you know what I'm talking about. The multivariate is much more analytical than the bivariate or univariate. So today we're going to look at why we need to use regression analysis. We will look at some examples. An important part is to look at the equation, how to express regression in equation. And we're going to look at the relationship between regression and correlation. Remember from last week, we talked about correlation. Correlation is actually the basis, the basic evidence that you need to have in order to go to regression analysis. We'll show you how to test hypotheses using regression and how to interpret the outputs from regression And we're going to look at the difference between simple and multiple regression and also logistics regression very quickly. And we're going to very quickly touch upon the concepts of multiple or simultaneous multiple regression in what we call structural equation modeling. And we will have a dedicated lecture on structural equation modeling in week 9. So why do we do regression analysis? Because we want to predict something. We want to verify or confirm the relationship between two or more variables. So typically in a regression analysis, you always ask this type of very broad question like, can I use a number of independent variables to predict an outcome? Can I use a number of different independent variables to predict a number of dependent variables, right? So you are interested in which variables, right, as the IV, which variables are significant statistically, okay, and how large is the magnitude of each of these variables in predicting the dependent variable, right? How large or the magnitude, and secondly, the direction. Is it positive? Is it negative between this independent variable and the dependent variable that it is trying to predict? So we have talked about positive or negative relationship in correlation. In a similar way, we can also see this in regression. Let's have a look at the next slide. So why do you use regression? When do you use regression? Typically, people use regression because you have some theory to test. Remember, we have talked about theory testing from week 1 and week 2 and even week 3, right? So in this week 4, we're very interested in using regression to test theory. For example, you might have a theory that you are interested in what makes children to have a healthy psychology, right? Psychological development of children is very important, right? And you might have a theory from a literature that you read just now that when the parents have a very family-centered care, which means that the family play a lot of role in there, then this will increase the children's psychological health. But then you read more literature, and you find out, hey, it's not just the presence of family-centered care that predict the child's psychological health, but there's also the parent, the role of the parent. Maybe are the parents having good psychological health themselves, right? That's your model too. And maybe you then reading the literature and you reflect on your own experience, and you even interview some psychologists and some parents, and you start to say, hey, it also depends on another very important variable called self-efficacy. Self-efficacy is very similar with confidence, self-confidence, right? So then you have a model 3, which says that this dependent variable called child psychological health can be explained by family-centered care, the parent's psychological health, and the self-efficacy belief of the children. So this can predict the child cycle. And then you have even more complex one after reading more, and maybe you have done some pilot study, a very small study, and you come up with model 4, which is more complicated, in which you think that the parent psychological health is not just an independent variable, but it becomes a mediator. And the self-efficacy is not just a very simple independent variable, but it becomes a mediator between family-centered care and psychological health. So from family-centered care, you theorize that family-centered care need to increase the self-efficacy belief. And when self-efficacy belief is increasing or reducing, it can affect the child's psychological health up or down, right? And you found that there's another variable called child spatial healthcare status needs. So it depends on whether the child has a special needs or not. So you can propose different model and you can test it. So long as your model is reasonable and is grounded on some theory, then you have some basis to test this. So let's dive a little bit deeper in terms of what is a regression. Let's say you are selling umbrellas, right? You're selling umbrellas somewhere, right? And as you sell day by day, and particularly, let's say there's a time when you have a lot of rains, right? So the rainy days, right? So when the rainy days come, in which you have more rainfall, you actually sell more umbrellas, right? So how do you pick this in terms of regression? So rainy days, exactly your predictor or your independent variable, which you have it on the x-axis, right? And how many umbrellas that you have sold, that is your y, or your dependent variable, right? So you wanted to see the relationship between this x and y, like whether rainfall can predict how many umbrellas that you can sell. Let's say those blue dots are the transactions that you have every day. Let's say on a particular day, when the rainfall is, let's say, about 78, you only sell around 15 umbrellas. On other days, when the rainy days was around 100 and, I don't know, 105 or 108, you have sold 32 umbrellas. And let's say on other days, the rainy days was around 147 and you sold 48 umbrellas. So every blue dot represents the sales that you have, or it depends if you want to survey a lot of umbrella sellers, right? Each dot is every respondent that you have, right? So in regression, what you're interested in is that red line that I've written, and this is actually called the line of best fit, or what you call the least square. And there's a formula behind this to calculate this. So in regression, you are interested in to find one line that best represent all the dots of observations or cases that you have in your data. So this is another way to look at the formula behind how you calculate that red line over there, right? So this equation, it looks a bit complicated, but it's not that complicated, right? So basically, in a regression, you are interested in the dependent variable. Dependent variable is that y. So if you express regression in mathematics, very simple mathematical equation, it has y, which is the outcome or dependent variable, equals to or is dependent on some variables that predict that y, that predict that outcome, right? So in regression, typically you have an intercept where your line will hit the y-axis, and this is what we call constant. You don't have to find out why, but this is always the case, right? So you have a line in your regression that hits. So if this is the y-axis, your regression line will always cut through the, like Ultraman, right? It cuts through the y-axis. And when it cuts through the y-axis, this is called the constant. The constant can be positive or negative, of course. And then you have the key independent variable that you are interested in, that you are investigating. Let's say x1. X1 is your independent variable. Let's say, for example, whether education level, which is expressed as x1, can predict salary. Salary is y, right? So you can survey 1,000 people, and what you want to estimate is that B1 and B0. Because if you enter in the equation, let's say you collect the data from 1,000 people who have filled in your questionnaire, and they give you how much salary did they get, they give you the y, and they give you what is their level of education. Then from just these two parameter or data, you can enter them into this equation to calculate B0 and B1. In B1, you're interested in that, what you call the slope of your line, whether the slope is very steep or very shallow, right? And constant is just where your regression line cuts through the y-axis. Right? So use the examples of the people who are selling umbrellas there, right? So y is the number of umbrellas sold, and this is the dependent variable. B null or B0 is the intercept. So that is when your regression line, the red line, crosses the y-axis. That means when what happens when the x is totally zero, right? Let's say when there is no rain, or when there is no rain, the x1, there's no rain, right? When this is null, what is that value or the number of umbrella people can sell? So when x1 is 0, then if you multiply 0 by anything, it will become 0. What you left with is the y and b0. So that means when x1, which is your independent variable that you're interested in, is 0, then you are left with a constant. So constant will hit the y-axis. So you're interested in when is your regression line hits or crosses or kisses the y-axis. The y-axis is the vertical one, right? And b1 is the slope or the magnitude. It tells you how big. So if you want to know how much is the rainfall is going to affect the umbrella cells, that the magnitude of that rainfall is determined by the b1, and this can be calculated automatically by Excel or using SPSS or R or whatever software that you are using to do the calculation. And x1 is just the variable that you are using to represent your analysis. So if you put it in visual form, the circles that you have are each data point. It can be a person, it can be an organization, it can be a group, it can be a country. So that's your data point, right? So you are trying to fit that line in the middle with a dot. Right? You also have some what we call confidence interval or confidence band. We're going to have a quick look on that later. So let's say you have two regression model, right? The one on the left, a lot of observations, and you have a blue regression line that fit it in. And the one on the other side, you have also fewer red dots or fewer observations, but you have that blue line. Now tell me which regression model better fit with the data or better explain the data. Of course, right? The answer is the one on my right, because you can see the blue line is so much closer to every of those red dots or observations, right? So it can better represent the variation of the data, while the one on my left, even though the blue line is kind of like nicely fitting in the data, but the data are quite spread. So your regression line is not able to capturing as precise information as the one on my right, because you can see later in the calculation there's what we call residuals. So residuals is eventually a form of error. So when you have observation that is far away from the blue line, you can see this as a much bigger error. So how many observation is so much further away from the blue line? It means like how much is the bigger? How much is the error? So you have a lot of error. While the one on my right, you can see the distance between every dot from the blue line is so much shorter. So the error overall is so much smaller. So this is another way to look at regression. You can calculate regression equations in Excel. Let's say you have a very simple data, right? You have variable X, let's say education level, how many years you have studied, and Y is the income, right? Let's just give some number, right? You can calculate it using the formula that I've shown you earlier. You can have X, look at the one in the middle, you can have X, exactly copy X and Y into column B and C, right? And you calculate XY, in which you multiply X and Y. So for example, you have 2.6, that is a multiplication between 1.0 and 2.6. And in Excel, it's super easy, just equals to B3 is 1.0, star was multiplication by C3. C3 is 2.6, and it will automatically give you 2.6, and then you click that cell and you range it, just drag it, and the formula from cell D3 that you have just created for the multiplication for X and Y will be totally copied down there. And the same for X squared or X squared, or the X multiplied by X multiplied by X, 1 multiplied by 1, 2, let's say B4 is 2.3, right? The value is 2.3. So 2.3 multiplied by 2.3. So you just say equals to X to the power. You don't have a spatial function. It has to have like a hat in your keyboard, right? So you have equals to B4 to the power of 2. Then you get that. And you repeat that, copy that down, and repeat the process for the y, and you go to the n, and you get a sum of x. Sum of x is the addition of all x, which gives you 23.1. Sum of y, or sigma of y, is you add column C3 to column C8. So they give you 23.6. You just click one function, it gives you the total value. And sum of x multiplied by y, which is, I think, 23.1 multiplied by the sum of, you have a column D you have xy on top, D3 to D8. So you add them up, that becomes 103. And you also have the sum of x squared from E3 to E8. You just add them up, and that's give you 110. And you do the same for y squared. And then you enter in them in the calculation of the sum of x, you square them, right? The sum of x, you square them. Oh, I'm running out of battery. Let me try. Sorry. I want to replicate by hand, but basically this is the formula. You just enter the formula, and then you just do the sum for the sum of y and square them, and you can calculate slope. So the Excel can fit in that line and give you a result. So what you need to do by hand is to enter the equation, which is y equals to 0.5 blah 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 plus what, and the r squared. What is the value of r squared? So let's have a look further. So I mentioned early on that regression builds on correlation. So correlation is the first evidence that you need to have in order to understand the relationship between two or more variables, right? And then the normal technique that I've just mentioned to you in terms of how you calculate that regression line is called ordinary least square. So the formula that I've shown you is called ordinary least square. So in ordinary least square, you're interested in finding the smallest distance from every observation from a line that best represent all these observations. And you also will have this. We can have a look at the relation between the correlation and the regression, the R square later. So remember from last week, we talked about the statistical procedures. So this week, we're going to look at a simple regression and multiple regression. So when we have only one independent variable and we have continuous dependent variable, let's say you are predicting how many years of education as your independent variable to predict that on people's income. Income is a metric or continuous variable. Then you use simple regression, just two variable, right? But let's say you have, you want to predict people's income. Again, income is a continuous or metric variable, which is any number in dollars, right? And you want to know whether gender, whether years of education, work experience, what else? The GPA, and a bunch of other variables. So you have multiple variables here. So if you have multiple independent variables and you have you have a dependent variable, which is metric outcome, then you can use multiple regression. Or even you have more than one dependent variable. So that's fine. And we're also going to look at the logistics regression, in which you have a single. If you are using binary logistic regression, you have a single independent variable, but you have a categorical outcome. You're going to look at it near the end. So importantly, why do we do regression? Because we want to test hypotheses, right? So what we do before we even use regression is you should have already stated your hypothesis. Remember, we talked about this 2 or 3 weeks ago. We draw the boxes and the arrows to depict our research model or and the relationships, and we express this relationship in sentences, such as, this variable is possibly associated with that variable. So that is called expressing your hypothesis. For example, age is possibly associated with salary level, or years of education is associated with salary level. So this is called expressing your hypothesis. So after you state your hypothesis, then what you do, you collect your data, right? You can use survey or experiment or whichever method, and then you collect the data, you verify your data, check for anything that is strange or missing value, and then you can do your regression analysis. Now, before you even do your regression analysis as your step one, so actually this is very simple two-step, but this step one has two components. The first part before you even do your regression is to check the assumptions, because regression depends on a certain assumption testing, which means that your regression has to pass this assumption test. If it doesn't pass the assumption test, basically your results will be very suspicious. Your result will not be something that people can trust on, or people can really rely on. So the first part is to check your samples. Do you meet the minimum sample requirement? That is always a very important part. So I look at many literature. Some of them, a lot of them is talking about the rule of 15. And what this rule of 15 means, your sample size depends on how many independent variables. Remember, you have independent variable to predict your dependent variable. So they say it depends on how many independent. Let's say your independent variables, you have 10. You have 10 independent variables to predict people's salary, right? It can be age, gender, years of education, where they studied, prior experience, blah, blah. So you have 10 independent variables. According to this rule is that you need to have at least 15 times 10. You need to have at least 150. You need to have 150 minimum sample to test this regression, right? So it cannot be too small. If you have a sample of only 10 people or 50 people, then your result may be suspicious, right? So you need to have this sample minimum. But some literature or some scholars use a rule of 20. Some even use 10. So there's a bit of a convention here in statistics. So pay attention to your field, your discipline. What is the usual sort of rule of thumb in terms of calculating the sample requirements? There's also a way to calculate sample requirement using power test, and there's a software called the G power, right? To check the statistical power, whether your sample is strong enough to detect some effect or not. So that's a separate discussion. We can have a look at that later. The second one is to check whether your data is normally distributed or not. So this is a key assumption. Remember, we talked about this last week when we discussed about the descriptive statistics. So the normality assumption is your data looks like a bell curve, like very nice, or at least close to this nicely shaped bell curve, right? So if your data is very skewed to the right or skewed to the left, positive skew or negative skew, or very, very slim or too flat in terms of its curtices, then you need to take some action, right? And then outliers, you need to check if you have some outliers. Outliers are very important. And one way to do this is to use Mahala, non-persistence or residual scatter plots. I like the scatter plot because they give you a visual description whether you have a serious outliers or not. Actually, the box plot is another tool that you can use to look at outliers. And this is from the lecture on descriptive statistics last week, right? Have a look at that video. And check for multicollinearity. How do you know if you have multicollinearity? What is multicollinearity? So multicollinearity is when you have too high correlations among the variables in your study. For example, you have 10 independent variables to predict people's how high is people's income. What variables predict how high people's income are, right? So when a lot of your variables, a lot of your independent variables is too highly correlated, this is something that you want to avoid. So multicollinearity will work against your data. So you don't want that. And what is considered high? So some literature says more than 0.7 or more than 0.8 is considered very high. And of course, you also look at the statistical significance, the p-value of the correlation. Typically, this is provided by you by the statistical software like SPSS or R, right? And then you check for other what you call collinearity diagnostics. So this is a term used in SPSS. For example, you check the tolerance value or VIF, variance inflation factor. So when you have a certain value that exceeds or give you this red flag, hey, there is a multicollinearity, then you have to be careful. And then once you pass this some testing, you do the regression analysis and you check for the results. So you are interested in the correlation, and there's a good first evidence or proxy for regression, and you check the R square, you check the F ratio, you look at the improvements in R square if you do your regression testing in a step-by-step or hierarchical manner. And you also look at, very important, the beta value or the coefficient that determines the how important of each of these independent variable that you are testing to predict the outcome variable or the dependent variable. And you look at the p-value is also very interesting. And once you have done this thing, then you make a decision to say that, well, according to our research, we have done this analysis of this sample size, and these are the results. At the end, we accept the alternative hypothesis, and thus we reject the null hypothesis. The null hypothesis is always like there's no relationship between the variables that you're testing, and the alternative hypothesis is always saying that there is a relationship of the variables that you are testing. For example, if you say these 10 variables are used to predict people's salary, and you say, well, the study confirm or offer support that maybe gender or years of education predict people's salary. And you can also do further tests, such as comparing groups. For example, you want to do whether different gender differ in terms of their salary, right? You can do a t-test, right? Or you can do a more complex one, for example, using ANOVA. And we're going to look at this later more. I think it's 2 weeks from now. We're going to look at the t-test, ANOVA, and MANOVA. So one thing when you are looking at your regression output is looking at the scatterplot. So I like to do scatterplot check because it gives you a very nice sort of visual overview of the relationship of the variable. For example, you want to see whether age of the employee is related to the salary. So you have, let's say 1,000 people filling your questionnaire, and you ask each of them their age and their salary, and that little circles there every person that fill in your survey, right? And what you can observe there, if X is your age of employee and Y is a salary, which is your dependent variable, and X is your independent variable, you can see a line there, which means the line goes up, right? Which means that the greater the value of X, also the greater the value of Y. Look at the line. So if you go to the right, as X increases, Y also increases, it goes up. So you can see there's a positive relationship between this X and Y. So how close is your data to the fitted regression line? And we know this from your model summary. So model summary is provided in your statistical packages such as SPSS or R. And model summary, what is actually model summary? It's just an overall summary. So remember, when you do the regression, the first thing that you want to know is overall, right? Overall, among all of these independent variables that you are testing, how much can they explain the variation of your dependent variable? Here we're using a very simple example. I think we're using a bivariate regression. So this ask will say, how well is your regression in explain the variability of the response? So how well is the variation of your, it's the same. How much is the variation of this independent variable can explain the variation of the dependent variable? Or how much is your dependent variable is explained by the independent variable? How much is the variation of the dependent variable can be explained by the independent variable? So for example, how much is the variation of salary of people in your sample can be explained by people's age or people's education. So R square is always between 0 to 1, or 0 to 100%, which is 1, right? So 1 is the highest, which means that if you have a value of 1.0, it means that every increase of the independent variable will be followed by every 1 unit increase of your independent variable will be followed by 1 unit increase of the dependent variable. So actually you can do the simple calculation. Look at the relation between R and R square. R there in the example is 0.379. If you multiply 0.379 by itself, 0.379 multiplied by 0.379, it will give you 0.143, and that is R square. 0.143, that is R square. So this R square is actually the square of the Pearson correlation coefficient that we have understood so far from last week's lecture. So what is R square further, right? So for example, you're trying to understand. So the first thing that you need to do when you look at this R square thing, right, in a model summary, look at the bottom. The bottom tell you what is the independent variable or the predictor. Here you have only one predictor, which is the age of the employee. So you're trying to use the age of how much is the age of employee can predict the changes in people's salary. So you can see here that the R square is 0.021, which means that what? 2.1% of the variation in people's salary, remember the salary is the dependent variable, can be explained by the age. Is that big or small? Well, we cannot tell because there's only one variable that you enter in this regression. So this is only a bivariate regression. If you enter multiple variable or multiple independent variable, not just age of employee, let's say you enter something else, then you have more information to see how big. But just roughly to look at 2.1%, I think is relatively small, right? Which means that only 2% of the variation of people's income in a sample can be explained by age. Right? So that means what? If only 2.1% of the variation of salaries can be explained by the age, the variable called age, that means there are 100% minus 2.1%, which is 97.9%. So there are almost 98% of the variation of the salary, which is the dependent variable, is beyond the factor called age. So there are other variables that we have not yet understood, that we have not studied. So this means that when researchers are trying to understand or to predict a dependent variable, they always use more than one independent variable, because when you have only one independent variable, you have very limited explanatory power. You have very limited ability to explain the variation or the changes in the dependent variable. So that means you need multiple regression. So in multiple regression, you have multiple independent variable. Let's have a look what happens to the R square when you have multiple independent variables. So this is okay. This is still the same example using the same analysis from the previous slide. Oh, sorry, this is another one. Look at that. Oh, sorry, it's still the same, right? Look at the age. Age is the predictor. Age is the independent variable, and the dependent variable is the salary. So the ANOVA tell you. So when you look at the ANOVA table, it's just telling you whether something is going on here between the age of the employee and the current salary. And typically there's a threshold value for F, which is it has to be bigger than 1. So what you see here is actually F is quite large, is 10 point something. And the key part of this is look at the significance, the P value. The significance is highly significant, which means that when it's significant, it really says that the model, the regression model that you are testing has statistical significance. It is significant, which means that the age in terms of its ability to predict the current salary. So this is a model, and this model is significant. And how do you know? Look at the F statistic, and it's significant. Significant is lesser than 0 at the significance of 0.001, or 0.1%. So F statistic, there's a formula to calculate it, which we're not going to go in deeper details. But I think when we go to a class on ANOVA, it's very closely related to the F statistics, and there's some simple calculations behind that F test. So slope. So how much is your independent variable? How much can your independent variable predict your dependent variable? And this is the most, I think, the most important thing that you want to know as a researcher, because you want to know to what extent is my variable predict my independent variable, predict my dependent variable. Right? So in this study, you are interested in whether your age of employee, how much can age of employee predict salary or current salary as a dependent variable. Right? Look at the bottom, dependent variable is current salary. So you can see there, actually the age has negative. So you can see the intercept. So when you look at this variable, when you look at this table, the key part is looking at the B0. What is the B0? B0 is the intercept. B0 is the intercept. Remember the equation that I showed earlier? So the intercept between the regression line with the y-axis, that is called the constant. The constant is the same as B0. So it shows there, regardless of people's age, the salary is 16,911, right? And then when you have people's age, eventually people's age have a negative relationship because it's minus 84.5, which means that every unit of change in X, or every unit of increase in people's age, employees' age, it produces a minus 84.55 change in the salary. So this is actually a negative relationship. Makes sense, right? So actually, when people are old at a certain stage, the salary is actually even going lower. But I think the relationship may not be very linear. It may look curvy linear. So this is just one example of how you looking at how you interpret the coefficients. And do we look at unstandardized coefficients or the standardized coefficients? So this is something that we can look at. So using the same example that we looked at early on, if you have actually only one independent variable, you can use unstandardized coefficient easily, right? So what if in your research you have multiple independent variables, and each of these independent variable is measured differently in terms of the format of the measurement? Maybe some of them are metric. Maybe your age is measured as a metric scale from, age 1 to age 95 for people's age, and then you have maybe people's years of education, which is also metric, from 0 years to 20 years, 30 years, and you have something that is like whether they have whether they have worked in the same industry or not, and that could be actually 0 and 1, right? And that is a categorical. So you can have different type of variables that are measured in different ways, but it's difficult to compare them one by one. But if you want to compare them, let's say you have different variables, and the variables are measured in different ways, looking at the standardized coefficient is allows you to kind of like standardize all of the variables in a similar way, and you just look at the standardized coefficient. So it gives you easier comparability across different variables. And of course, you still look at the significance level, right? So this is another example from one of the readings that we have. Right? You can look at, so they're trying to understand out of different type of public service motivation, which is people's motivation to serve the public, what are their relationship? Can they predict people's commitment to organization, people's job satisfaction, people's job motivation, etc., etc.? And then they use this self-sacrifice subscale, commitment to the public interest subscale, and attraction to public policies making, and compassion subscale. So they have these 4 different motives for public service to predict them. Look at that, because they use different scale and some are there's normative, some are rational, some are effective. Their measurement format, let's say interval or metric or ordinal, whatever, or even 0 and 1 in terms of categorical measurement, you cannot easily compare this. So that's why I look at in the table down there, their beta, they use a standardized coefficient. So, and another example, you are comparing, you want to study what predict people's science score, exam in science, right? Look at the bottom there, science score, right? So you're trying to predict science score using math score, the gender with a male, female, and the social studies score and reading score. This math score, female, the gender, the social studies score, and reading score, these are very different things, very different variables. And it's very difficult just to look at the unstandardized coefficient. So in this case, it's easier to look at the standardized coefficient. And you can look at, so standardized coefficient is actually using some form of standard deviation to see in a standardized manner how big is each of these independent variables can predict the outcome. The outcome variable is a science score, right? So for example, you can see that 0.368, that is perhaps the largest. So math score strongly predict and is significant, 0.000. So math score is the highest predictor of the science score, and reading score 0.347 is the second. So I think math score and reading score have something to do with perhaps people's intelligence in order to do well in the science score. But look at the social studies score, is 0.54 and it's not significant. So it could tell us that, you know, someone's test result in social sciences or social studies has nothing to do to explain or to predict the science score. So when you write up your conclusion for your regression, it's important to write down the equation for the regression. So for example, from the bivariate regression that we had early on, the dependent variable is current salary and the independent variable is the age of the employee. From the table that you have seen early on, one of them give us the constant and the beta value. So the constant, or the B0 or B null, is the intercept. So current salary is equal to that 16,111 minus 84.55 of the age employee. So let's say you have a hypothesis that age is negatively correlated with salary, right? And you have collected data, you test using regression, and you come up with this regression equation, current salary equals to blah, 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 blah. Then you can offer a recommendation or final summary to say, well, we tested a hypothesis using a random sample of how many subjects, and we regress the independent variable on the dependent variable. For example, the current salary was regressed on the age, and our model R-square is 0.021. Remember from the previous table that I've shown you, it's only 2.1%, and it's significant. And you write it in terms of F and the degrees of freedom. And look at the tables early on. There's one that have 1 and 472. So the F and let's say F1 472. Yeah, so this one, the degrees of freedom is 1. Look at the one in the middle, DF, degrees of freedom, 1 and 472. So you're looking at the degrees of freedom of the regression and the residual. So 1 and 472. So the F test for 1, 472 equals to 10. So the F test value is 10. F test is 10.267 and it's significant 0.001. So regression coefficient is negative 84.55, significant at 0.001 level. So regression support the hypothesis 1, that is, it provide evidence that age is negatively correlated with salary. So that's how typically you report your results. So I stop it there for very simple bivariate regression.